Welcome to an overview or fundamentals video on the HART protocol. This video will cover the history of the HART protocol, the HART protocol theory of operation, HART communicators, working with devices using a HART communicator, and Det-Tronics HART protocol documentation. Let's get started. It is always helpful to know how we got to where we are at. So let's look at the history of process industry instrumentation technology and protocols. There has always been a need to get the measurement of a device from the device to a remote or centralized location. In the 1960s, this was done using a pneumatic signal, typically 3 to 15 psi. In the late 1960s, analog electronics were introduced to the market. There was only one variable available, but a variety of signal values, 0 to 16 milliamps, 0 to 20 milliamps, 4 to 20 milliamps, and 10 to 50 milliamps. The industry settled on the 4 to 20 milliamp signal to be the standard. In the mid-1980s, low-power microprocessors became affordable enough to put in instrumentation. The term SMART was used when referring to these devices. They had a lot of computing ability to be able to provide multiple variables and diagnostics. The challenge was figuring out the best way to get the information out. The HART protocol became the industry standard. The background on that is covered on the next slide. The HART protocol was slow and could only provide up to 4 variables. The industry was wanting to get more information and faster out of the device. The next wave of technology for instrumentation was fully digital instrumentation with multiple sensors and advanced diagnostics. And like most things in our industry, there was the US line of thought and the European line of thought on what a fully digital device and protocol should look like. The US adopted Foundation Field Bus, which had the capability to do control in the field or control system functionality in the device, and peer-to-peer communications. European manufacturers adopted Profibus, which, similar to HART, just provided the variables and diagnostics to the host system to make controlled decisions much faster. Both were complicated in multiple ways, leaving the industry looking for an alternative. Wireless was the next wave of technology. It was touted as being able to get up to 8 variables and diagnostics with no wires. That was true, but update time was limited by wireless bandwidth and battery life, which in the end made it not viable to be used for control. What to do? In summary, the method of getting the measurement out of the instrumentation over the years has allowed an increase of functionality of the instrumentation. More sensors, more variables, more calculated variables, and advanced diagnostics. But the complexity has led most users to stay with the simplicity of 4 to 20 milliamps with HART. Now for just a little background on HART. Manufacturers were putting computing power in the instrumentation, but couldn't come to an agreement on how to get the information out. The technical term used at that time was stranded data. There was a race between many manufacturers to come up with a protocol for the microprocessor-based instrumentation. Rosemount's entry into the race ended up to be the protocol of choice, as it was simple and did not interfere with the 4 to 20 milliamp signal. Rosemount knew it was going to be a struggle for competitors to adopt HART, so they donated the protocol intellectual property and governance to the HART Foundation, which has morphed into what we know today as the FieldComm Group, the keeper of many protocols and technologies used in the industry. The FieldComm Group is also where manufacturers get their devices certified that they meet the standard, and is an industry resource for a multitude of device drivers. Now let's focus on the HART protocol. You just learned that the HART protocol has been an industry standard for many years. The primary reason it was selected by the industry was that the HART signal did not interfere with the 4 to 20 milliamp output of the device. How that works is there is a special HART modem that superimposes the HART signal on the 4 to 20 milliamp signal by modulating the digital data plus and minus 0.5 milliamps. The net result of the modulation is 0, thus not interfering with the 4 to 20 milliamp output of the device. Now let's see how that works. Now let's learn how the HART signal is developed and read. Here is a basic 4 to 20 milliamp loop. The measurement changes, the milliamp output changes. You just learned that the HART signal was superimposed on the 4 to 20 milliamp signal by modulating the existing milliamp value plus and minus a half a milliamp. The reason the HART protocol became the industry standard is that you can only measure milliamps in series, which means you would have to disconnect wires and place the reading device in the loop to read the milliamp modulation. Not very friendly and maintenance intensive. This is where the required 250 ohm load resistor comes in. As a HART signal passes through the 250 ohm load, it is converted to a voltage signal, and voltage can be read in parallel, so you can connect a communicator across the load to read the signal. Now the superimposed milliamp signal is converted to a voltage signal, which the communicator can read. So, the rule is that you need to put the load resistor where you plan on connecting the communicator. You might find devices communicating at the device that don't have a load resistor. This is because most systems already have a load in the loop, as most I/O inputs to systems use a 250 ohm load as they read voltage instead of milliamps. So you could connect across that load, but not very friendly as the input to the system I/O is typically not close to the device, and most sites don't allow I&E technicians to mess around in the system marshalling panels. You must install the load at an accessible location if planning to communicate remotely. HART devices have an address that ranges between 0 and 64. Most users don't know this as communicators come default to search for address 0 when connecting, and very seldom do you come across a device with an address other than 0. In HART protocol, address 0 means the device's output, or primary variable, is going to be represented by the 4 to 20 milliamp signal, which is well over 99% of the installations. The HART protocol does support multiple devices on the same set of wires. It is called the multidrop mode. In the multidrop mode, each device is assigned its own address, so the host knows which device it is communicating with. And there is no need for the milliamp meter, as each device locks its output at 4 milliamps. This mode works, but 1. It is not an approved configuration for SIS applications, and 2. It is very slow. HART protocol is slow, and then all these devices must share the same set of wires, which makes it extremely slow, so not used very often. One application where you will see addressing used is when a wireless adapter is connected to the HART device. The wireless adapter is a device that allows a 4 to 20 milliamp device to continue to output a 4 to 20 milliamp signal while simultaneously transmitting variables and diagnostic information using the wireless HART protocol. The device remains at address 0, 4 to 20 milliamp output. The wireless adapter is address 63. The communicator needs to be configured to look for address 0 and address 63. Once connected, you will be given the option of which device to connect to. Now to HART variables. There are 4 variables. HART 7 has a few more variables, but they are called dynamic variables, and there is no need to address them here. The primary variable is most commonly referred to as the PV. This is the value that is represented on the 4 to 20 milliamp output. It is a fire or no fire. It is the percent LEL. The gas leak or no gas leak. The other 3 variables are technically called the secondary, tertiary, and quaternary, but most commonly referred to, because they are hard to spell and pronounce, as the second, third, and fourth variable. These are secondary or nice-to-know measurements, such as the device temperature. They are only available digitally. There have been 3 HART revisions over the years. The original release was HART 5. The most common complaint of HART 5 was the tag field was limited to 8 characters. HART 6 was the next release. It had all the functionality of 5, plus many new features, but most not useful for the typical user. The main attraction to HART 6 was the 32-character tag, known to the user interface as the long tag. Not many manufacturers manufactured HART 6 devices, as most knew the HART 7 standard was going to be released soon. HART 7 is now the current release. It includes all the functionality of HART 5 and 6, plus wireless HART. Device drivers. Similar to printers, each device and each revision of the device needs a new driver. If a manufacturer adds functionality to a device, a new driver needs to be made to access the new functionality. These drivers are created in different forms to cover all the industry needs. The original device drivers were written in the HART device description language. It is a simple text-based interface. Customers demanded a more graphical user interface, so the HART Foundation published an Enhanced Device Driver Standard, or EDDL. This standard has built-in graphics, like gauges and status graphics. The manufacturer could select graphics out of a selection included in the standard. Some manufacturers provided drivers using the graphics available in the EDDL language. Most, including Det-Tronics, stayed with a text-based user interface. Meanwhile, Europeans, tired of the limitations of available device description languages to develop a more meaningful user interface, and high prices of interface tools, developed another user interface standard, the FTT DTM technology. In the simplest of terms, the system is very similar to how HART communicators work. The FTT is called the frame. It is a PC-based operating system similar to that in the communicator. The DTMs are the DDs. The same rules apply to DTMs as the DDs. You need a new DTM for every revision of every device. The big difference is that you need to build your own system. You install the frame, and then you add the DTMs you need for your devices. There are advantages and disadvantages to this system that will not be covered here. What makes this system attractive to many is that it is free. The frame is free, and the DTMs are free. Handheld HART communicators are the most common tool to be used to communicate with HART devices. There have been different attempts by different manufacturers to enter the communicator market, but Emerson has dominated it from the beginning. And over the years, there have been many revisions of the Emerson HART communicators. The most noticeable difference is the form and the size of the display. Technically, the changes have been driven by the need to increase the memory so it can hold more DDs and how the DDs are added. The most current revision, which is the TREX, is an exception. It has a much larger screen and a lot more functionality, or upgrade opportunities, was added. Support for Foundation Fieldbus and apps such as the PDF viewer to read instruction manuals, Fieldbus diagnostics, a calculator, and Fisher valve link. There is a lot more inside the TREX, but the three major components are the modems, the operating system, and the device drivers. The HART modem is standard. The Foundation Fieldbus modem is an upgrade. The TREX is shipped with the current operating system, optional apps, an Emerson selected DD library, and a minimum 1-year, 3-year optional support. This support includes a subscription that allows the user access to new operating systems and the complete FieldComm DD library using the Emerson Upgrade Studio software. Upgrade Studio is hosted on an Emerson cloud. It connects to the TREX using a USB cable. It allows the user to get updates to the operating system, DDs, and apps, download updates and apps, and also manually download DDs. So anytime a customer is needing an update to access new functionality or a new DD, the first question to ask is if they have an Emerson My Account and Upgrade Studio. There are only two things that can cause a HART communicator not to connect to a device. 1. If for some reason there is no HART signal due to no load, no power, connected incorrectly, whatever, when trying to connect, the TREX simply indicates there is no HART signal. This is not a DD problem. It is something else. Second, the TREX indicates you are connected to a generic device. This is a DD problem. You do not have the correct DD loaded into the TREX. Generic means that the TREX knows it is connected to a HART device, it just doesn't know what it is. You, or they, need to either get the new DD downloaded from Upgrade Studio or get the new DD from the manufacturer and download it using Upgrade Studio. If you know your customer is going to get a new product and you want to make sure they have the DD to communicate with it, you can check what's in the TREX DD library, having it not connected to a device, and following this procedure. Select Field Communicator, HART Offline, Offline Configuration. A listing of all the DDs in this TREX is displayed. Swipe up or scroll down to the manufacturer you are interested in. Select it. A list of that manufacturer's DDs loaded in this TREX will be listed. And then click on the particular device you are interested in to get more information. The description of the DD revision is cryptic, but you can contact support and they can tell you more. Now, let's look at working with HART devices. Here is a diagram of a HART device and a 4 to 20 milliamp loop. It all starts with a sensor. For Det-Tronics devices, it would be the sensors built to detect a fire or to measure the LEL of a gas. The output of the sensor goes to an analog to digital converter. The analog to digital converter turns an infinite number of possible analog values out of the sensor to a discrete digital value. The A to D converter then sends the digital value to the microprocessor. The microprocessor takes the inputs from the user configuration and diagnostics to determine what the milliamp value of the device should be. It passes that value on to the digital to analog converter, which controls the device's milliamp output. This basic block diagram works well for all HART devices, no matter what it is trying to measure. Now let's look at how these values are displayed on any HART interface. In this case, a TREX will be used. 0% LEL is being applied to this sensor. The PV value displayed in the TREX is the calculated value from the A to D. If the PV displayed on the TREX is not the value of the PV being applied, a sensor trim, sometimes simply called a calibration, needs to be performed. The analog output value displayed on the TREX is what the microprocessor is telling the D to A to output. Here, it is important to understand that the TREX or any HART communicator is a purely digital device. It can't measure the milliamp output, and there is no feedback loop in the device. It is simply displaying the value the microprocessor is telling the D to A to output. You need to compare the actual milliamp output of the device to the milliamp value displayed on the TREX. If they don't match, and you are sure the milliamp meter or whatever is measuring the milliamp output is accurate, you need to perform, dependent on the manufacturer, an output trim, sometimes called output calibration, and sometimes, Det-Tronics, a D to A trim to get them to match. Now a quick practical. What needs to be done here? First, check the calibration, as if it is not correct, the output will not be correct. That looks good. Now check the analog output. Here is the problem. If you are sure the milliamp meter is good, a D to A trim will fix this. Now on to the last topic, Det-Tronics HART documentation. Some Det-Tronics detectors have instruction manuals dedicated to the specific HART protocol implementation in that device. Some cover the implementation inside the standard instruction manual. One of the more requested pieces of information is for the device menu tree. These trees show the user how to find or navigate through the information or procedures for the attached device. For example, if you wanted to find the range values, you could find them on the tree and work backwards. Here are the range values. You back up and see range values in the Basic Setup menu. I go backward again and find the Basic Setup menu is under Device Setup on the opening screen, sometimes called the Root menu. So if I wanted to find the range values of this detector, I would start by connecting to the device by selecting Field Communicator. HART is detected, so the TREX is communicating with the detector. That is always a good sign. Here is the opening screen. If there were any alerts or alarms, this would be showing. It is not, so another good sign. Select Device Setup, then Basic Setup, then Range Values, and here they are. Upper and lower range values. And this is the screen where you can configure them, as the pencil indicates a configurable field. Navigating through a HART 5 device is different than a HART 7 device, and then each revision of each device could have a different menu. So you need to know that you have the correct tree. Some trees are clearly marked which revision this tree is for. Others are not marked. The easiest way to figure out if you have at least close to the correct tree is to look at the Root menu, or the opening screen on the TREX when connected to the device, and compare it to the tree you have. And then one last piece of information. Sometimes it is nice to know whether this is a HART 5 or HART 7 device. The easy way to tell is by looking at the Root menu. A HART 5 device opening screen will have 5 selections similar to these. A HART 7 device will have 3 selections similar to these. This video was developed by Det-Tronics Educational Services. Here is the contact information if you have questions or would like more information.